We're going to now solve the heat diffusion equation to determine the actual temperature distribution in an object. We're going to do this for the example of a window. Our goal is to find the non-dimensional temperature distribution in a window, which is held at T1 on one side, this would be the hot side of the window, and T2 on the other side, the cold side of the window. We also will determine the heat flux and the heat current for the cross-sectional area A. The assumptions that we will apply is that we are at steady state, that this is a one-dimensional problem in which we are solving for heat transfer in the x direction, that we have constant thermal conductivity, and no generation term. In other words, the window itself is not creating heat. We establish first a simplified governing equation. So we start with the general form of the heat diffusion equation. We apply the assumption that we are solving a one-dimensional heat transfer problem, that there is no generation of heat within the system itself, and that we are at steady state. And with these assumptions, we end up with a much simpler governing equation. We can now solve the system subject to boundary conditions. We integrate the governing equation. We end up with this expression, which has two constants, A and B. The two boundary conditions that we have are that the temperature at x equals 0 is T sub 1, and that the temperature at x equals L is T sub 2. If we apply both of these, we get expressions for constants B and A, that B equals T1 and A equals T2 minus T1 over L. And if we plug in, we now have an expression for the temperature distribution, that T of x equals T2 times x divided by L, plus T1 times the quantity of 1 minus x over L. It'll be useful to non-dimensionalize the equation that we just found. It'll help to simplify this equation even further. So we start out by defining dimensionless groups. We define a dimensionless temperature, theta, and we specify that theta equals T of x minus T sub 1 divided by T sub 2 minus T1. This means that the temperature at any given point, we then subtract T1, and we normalize this against the maximum possible temperature difference. So this is a parameter now which ranges from 0 to 1, which is what we desire for a dimensionless group. We define eta equals x over L, so we now have a dimensionless distance, which also ranges from 0 to 1. We take now the solution that we just found a moment ago, we rearrange it, and we see when we rearrange it that these dimensionless groups naturally come from this equation. What we end up with then is simply that theta equals eta, a remarkably simple result for this problem. So now that we have the temperature distribution, we can now find the heat flux. So we start with Fourier's law, and into Fourier's law, we need to plug in for dt dx. We fortunately have that temperature distribution. So we plug in, and we find that qx double prime equals kx over L times T1 minus T2. As we thought about earlier, this is a constant, and this means that the flux itself is spatially invariant from x equals 0 to x equals L. We can now also calculate the heat current. That, of course, requires simply taking the flux and multiplying by the cross-sectional area A. And we end up then with kx times A divided by L times T1 minus T2. We can rearrange this. And the physical significance of the rearranged form that you see right here, we will discuss in just a moment in the equivalent circuit section. So to summarize our strategy, we started with the PDE, we applied assumptions to make it into an ODE, we then solved that ODE, subject to our boundary conditions, and then applied Fourier's law. And this is a very general trajectory for these sorts of problems that you will see time and time again.